Yes, sir. Yes. I do have a question about Hilbert axiomatic method that you called it in a certain point of your lecture. My question is this. You believe that Hilbert axiomatic method is the synthetic method or has something to do with Aristotle analytic synthetic method? Why ask this question? I don't know if I misremember, but in your Le ragioni della logica, in a point you seem to say that Hilbert axiomatic method was something close to Aristotle analytic synthetic method. I don't know if you changed your mind about that. First. Second, if it is the synthetic method, it is the synthetic method because of that sentence that you said when you say that axioms are in a way arbitrary. No? But and the question is this: you take this statement, axioms are arbitrary, from the Frege-Hilbert discussion, or you have any other historical source to take that? Because if you take it from the Frege-Hilbert discussions, that discussion is close to the role of axioms in geometry. And Hilbert had one problem to justify non-Euclidean geometry, right? Which had no empirical basis. But Hilbert believed at the same time that Euclidean geometry at that time had a strong empirical basis. So why say that? Because he has to give a definition of axioms which takes, grant the either the Euclidean geometry and the non-Euclidean geometry. But Hilbert believed another point, that there was a pre-established harmony between thought and experience. So for Hilbert was no problem to say that axioms are formulated in an arbitrary way, because sooner or later they will find an application in the empirical world, which is exactly what happened with Einstein's relativity. So my question is this, because I firmly believe that Hilbert axiomatic method is something close to the analytic synthetic method. What you say about that?
Yeah. Okay. Let us distinguish between Hilbert 1900 and Hilbert 1922, right?
Okay.
Hilbert before formulating his program, and Hilbert a foundationalist, right?
Okay.
In 1900, in the famous paper Mathematical Problems, he was a mathematician. So he was narrating what was his practice. In fact, he says, I consider two procedures for obtaining conjectures: generalization and particularization. He indicates two methods, right? But he was a mathematician, was describing his practice, his own practice, right?
Right.
Then becomes rubber, violent. They contest, all mathematics. They say mathematics is nothing. It has to be destroyed. Then he has to defend mathematics. And he formulates his program. When he formulates his program, he has to change completely. He's no longer the mathematician. Of course, he's always a mathematician. But he has to defend this construction, as a religious thing. He uses very strong words, right? And in order to do that, he has to assume certain things. First of all, Hilbert is part of a movement at the end of the 19th century, which Dettingen was represented in this movement, which assumed that mathematics must be absolutely free. You know what Dettingen writes, right? Well, Hilbert uses almost the same words as Dettingen. It says that mathematics must be absolutely free, in all limitation and consistency. So it must be, as this in every paper, almost everywhere, he must be absolutely free to choose the axiom as he pleases, and then he has to prove that it's consistent. That's all. So I don't think this is limited to the first, but always, I should say here.
So by this you mean that there is a shift in Hilbert thinking from the analytic axiomatic, analytic synthetic method, for instance, when he
I'm not
to
sure.
the synthetic method?
No, I'm not sure whether in 1900 he was thinking of the analytic method. I don't think so.
Okay.
I don't think so. He was just saying that he uses as mathematician this generalization, so on. I think so. But I think the less known, when he has to use the axiomatic method, not as a method of mathematics, but as a method for serving mathematics from the attacks of Roman, well, then he has to use axioms in a sense and say, we both must be free, but has to provide consistency proof of the axiom. But you asked another thing.
No, I mean, there was...
Established harmony.
huh?
We pre-established harmony.
Yeah.
Oh, yes, yes, yes. Yes, that's true. Well,
I mean, it's a strong, in the Paris lecture, he starts with the pre-established harmony.
yes, yes. He says that the mathematicians think freely, and then by this harmony, what they think finds some application. That he knew very well that only a very small part of mathematics has application to it. So he was well aware of this, really. He knew that in physics you can apply only a small part of the mathematics developed at this time and today, and so he could not say that all mathematics, this harmony, is such that all mathematical theories are applicable at all. He didn't say that.
Not all sentences, because there is ideal part and real part.
Yes, yes.
Not all sentences of mathematics, but the theory as a whole, more or less, sooner or later,
No, but
will be applied.
Right.
For instance, he says this in twice, and there are 30 years between the first and the second time. So it is something that Hilbert really believed, strongly believed. He says in the 1900 in the Paris lecture, and then in 1930 when he was in Königsberg to be the Naturerkennen Logik. So it is something that Hilbert believed. It's true that he believed that it's not all mathematics, but not all the sentence of a single field
No.
in a mathematical.
He doesn't believe that all mathematical theories are true. He thought that some mathematical theories are true. He was a good mathematician. He couldn't think that. I mean, this is false. I mean, there are plenty of mathematical theories which have found more application in his century, in the 19th century. There are plenty of mathematics which now is no more, I mean, nobody studies it. Certain parts of mathematics simply disappear. Nobody cares about that. So he knew, he was perfectly aware of that.
Any questions?
Yes.
Yes, I just wanted to say something in defense of Punko. I think your argument against his...
Yes, it's not clear.
Sorry. Yes, I just want to say a few things in defense of Punko. Now, I think your criticism is quite valid if you consider him as proposing a completely general method for mathematical discovery, so I agree with it. On the other hand, I would like to defend him in the following way. Maybe there's a certain class of discoveries, which indeed I would call Meno-like discoveries, because they're rather like the discoveries which are, Plato discusses in the Meno, and maybe you can defend his view there. Now, the characteristic of Meno-like discoveries is that you have a well-defined problem, and you're able to recognize what a solution to it would look like. Now, if you want to solve such a problem, I think his idea in general terms is that you just fiddle around making lots of combinations, and then eventually you suddenly see one that actually solves the problem. Because you've got the problem clear, and you're able to recognize Now, what happens in the Meno is that actually the slave boy doesn't fiddle around. Socrates just draws the solution for it. But it's important because the slave boy does recognize that that's the correct solution. So if you didn't have Socrates there, the alternative method, and this is what I take Poincaré to be saying, is you just fiddle around making all these combinations. And if you're very good, if you're very used to doing it, your unconscious mind will do it for you. I mean, that wouldn't happen with me, for example, but with him, it clearly did happen. Or you could even do it by drawing on the board all the combinations. So you do that, and then eventually, sack, you see one, because you can recognize it, because remember there's the preliminary stage where you have to study the problem consciously before you can start. Now that seems to me not to apply to all problems, but maybe to a certain class of problems. So that's my attempt to defend Poincaré.
Yes, but you are considering a particular problem. I'm considering the general statement by Poincaré that all mathematics is like that. If you consider the solution of problems, his statements general, then it doesn't work. I said that this contradicts.
Well, no, I agree with you on that.
So
maybe there's a certain class of...
Maybe.
Conflicts that to a certain class of problem that
maybe.
needs position.
But I was interested in the general question if psychology or mathematics can replace logic or discovery. This is my...
But do you think there might be something in this idea for a particular class of problems, maybe?
Yes, but look, when I say that discovery is by non-deductive rules, for instance, most deductive rules, we apply most deductive rules, non-deductive rules, unconsciously. I mean, if you learn to go to a bicycle, at first you must be conscious, of what I'm doing, but after a while, you go without thinking about it. A dancer at first has to learn how to dance, and then it's the same in reasoning. We learn to use certain form of reasoning. At first it's very difficult to understand, then it becomes automatic. And when this is automatic, it's unconscious in a sense. Right? So there's no problem. My question is only this. We have to distinguish between intuition and this. For me, there is no intuition. There is unconscious use of this kind. Right. So I guess the idea that you remember poetic intuition, Popper. Right.
That's really
That would only apply to well-structured problems of the kind that Donald was talking about before, that you learn to solve a certain kind of class of problems and it becomes so routine, you recognize immediately what kind of problem it is, and so you don't have to consciously set out, now let's see, how did I do that? Oh, step one, step two, step three, you just solve it. But what about new problems that are not well articulated, not well formed, or maybe they are well formed, but it's a problem that you've never tackled before? You use the terms logic and rule and so forth, but it seems to me that you're interesting examples. And you look at the ancient mathematicians and very, very clever proofs of things, but you think, well, the very fact that they're clever meant it took imagination or something for them to set up the problem the way you did. Once it's set up that way, then you can see the analogy or the metaphor and so forth. But it seems to me it took a lot of cleverness or imagination to set it up that way. So.
When I speak about logical discovery, I don't mean only discovery of the solution to the problem, but also discovery of problems themselves. And most problems are generated by from previous problem, by generalization, or by analogy, and so on, by metaphor, and so on. So the rules I was talking about are not only rules for solving given problems, but also for finding new problems. Because all problems are found by some sort of analogy, induction, and so on. So in this sense, I think that these rules are both, serve for both uses, for finding solution and for finding problems.
So it's about... So okay, you answered my question. So my question was, before your answer, you have problem solving and problem finding, in a sense. So I'm using the technology of Simon. So you're saying that the same rules that you are giving in your talk, in your book, that I know very well. That I mean, they are part of me, and so the idea that using these rules you can define a problem. You're saying that.
Yes, in the sense that many problems are generated from other problems or from solution to problems. In the sense that you find a solution, then you realize that the problem was a special case of some more general problem, and you state more general problem and so on. So, in other cases, you have a problem, you find that by some analogy, a similar problem could be raised in a similar field, for instance. Well, in economics, but a lot of people use this analogical. Well,
This is the
physical models and so on.
physicist, yes.
Yeah.
Every physicist starts with a very simplified version of
Yeah.
the problem.
Yeah.
Once he's able to
Yeah,
solve it,
exactly.
they say, okay, now what if I
Exactly.
add some complication and the
Yeah,
next and the next?
I mean, well, I see maybe a little problem here, because I'm with you when you say I can apply these rules to solve problems, also to finding problems. But I'm not sure that you can find all the problems that way. I mean, if I think of your example, calculus, which you define as a real theoretical novelty. One of the most astonishing example of discovery, scientific discovery, in a strong sense. That means that from the bottom, from the data, using verbal reasoning, graphs, and so on, you generate a new mathematics. So, in that case, you're using. So I see many tools that are necessary to produce this new mathematics. You need graphs, you need verbal reasoning, you need a preliminary conceptualization of the problem. So, and maybe then you can apply your rules. So, my question is about this point. Maybe the point is that maybe you need a preliminary conceptualization of the problem. I mean, you have to find what are the variables, what are relevant or not. And so, I don't know if you can do that by using all these rules. I don't know. Maybe it's something you could write about. How can you find problems using these rules? Because, I mean, your picture about problem solving is completely right to me. So, that's the way by which you can solve problems. That's your point. I mean, I don't see how can reasonably object this picture. But maybe there is something that can be said, something more that can be said about problem finding. I don't know. Maybe and to find new problems. Yes, because when you're using analogy, metaphors, that you're using some sense conservative strategy. I mean that you're using what is known, is already known.
Even rules are not given us.
New rules. Okay, so you mean the set of rules is open?
I said, they are not rules set. Right? So, Bacon said, rules for discovery. The rules for discovery are discovered as research rules. Two things, they go together, right? So it's something, it's part of the progress of science, not only to discover the results, but also rules. So this is really the progress of science, I think.
Okay, so
The progress in methods.
Okay.
The logic of discovery advances discoveries or something.
Yeah,
Something like that.
yeah.
That was another different question.
This is a question about Fermat's last theorem, a rather obscure topic. We had a seminar about this in London given by Emily Grosshopes, and she gave an analysis of what Wiles had done, very much like what you said. There's no disagreement there. But one point that emerged is that if you consider the hypotheses from which Wiles deduces the result, they're actually extremely strong hypotheses. They're much stronger. Most mathematicians would accept Zermelo-Fraenkel set theory with the axiom of choice. But Wiles is assuming some things that are much stronger than that. So the question is, there's something funny going on, because most people assume that since Wiles has proved it, the theorem must be true. On the other hand, he's actually proved it from very general premises which are not generally accepted. So there's something a little odd going on here. I wonder if you'd like to comment on that situation.
Well, using very strong assumptions is very useful, because you make very short proofs. This is why Hilbert, for instance, said that ideal methods are useful because they make proofs shorter, that's all. In fact, his project was to show that every proof for the real result can be proved by real proof, even if you use ideal elements. Ideal elements make the proof shorter. So people use very strong assumption just because of that, because they make the proofs very short. That's all. Just for
There's no guarantee that you can prove it.
Of course.
The problem, the question whether there are simpler hypotheses or assumption under which you can prove a theorem is not always well defined. I mean, the history of mathematics showed that often the theorem was first demonstrated with very restrictive assumption, and then the assumption were gradually released, and you could find a more general demonstration of the same theorem under more general or less restrictive axioms. But then the question whether you can define one answer for all the minimal set of axioms that are needed to prove a given theorem, that is somehow not well defined, I think.
So is your idea that there, I guess not,
That there is a complete set of rules. I mean, the logic of discovery in your sense. That we keep adding the rules as we go along. Okay.
The work goes on, you add also new methods, new rules. This is Bacon's idea. I mean, it's very good. I mean, I found this idea in Bacon. The two things go together.
it is a good
Yeah.
There's a lot of good stuff.
Yeah.
But you just can't read new rules for discovery. Remember, his ideas have been used by the AI community very fruitfully, actually.
Yeah.
They've formulated
Yeah.
and formalized some of his conceptions
Yeah.
and used them for achievement. So he's quite relevant to
You can say
contemporary
it, you're not
technology.
speaking about your book about this. You can say this something about this in your book.
Yes, well, it's just a comment that Bacon's ideas, I mean, I discovered when I worked with the AI community for a while, that many of them are reading Bacon, a sort of 17th century text, formalizing some of his methods, and using them for machine learning programs, often quite successfully. So I thought this is very remarkable. I mean, here's someone who wrote in 1620, and nowadays, they're using them for machine learning programs in AI. So I think that's rather shows that there was something in Bacon indeed. I think we brought out that Bacon knew that Bacon was totally erroneous. This was a shock to me. But then life is full of shocks.
Other questions, comments?
Enough is enough.
Well, let's thank our speaker. So tomorrow morning, 10 o'clock. 10 o'clock.
Thank you for your
will do the difficulty.